The universe is hurtling toward a silent, final chapter, where stars fade out, galaxies drift apart, and all that remains is an overwhelming emptiness. It's a future so distant, yet so inevitable, that thinking about it forces us to confront the very meaning of existence. This isn't just science fiction, it's a scientific prediction rooted in thermodynamics and cosmic evolution. Stick around, because understanding the heat death of the universe might just change how you see the world and your place in it forever. The nature of cosmic expansion. The universe is expanding at an accelerating rate, driven by what scientists refer to as dark energy. This mysterious force constitutes about 68% of the total energy content of the cosmos and causes galaxies to drift away from each other faster over time. The process isn't uniform in the sense that regions of space farther apart recede more rapidly than those closer together, a fact revealed by observing the redshift in light from distant galaxies. Because this expansion speeds up, structures like galaxy clusters will gradually become more isolated, with the vast spaces between them growing larger and larger. As expansion continues, galaxies outside our local group will eventually drift beyond our observable horizon, meaning their light will no longer reach us. This pushes the universe toward a state where, on the largest scales, it looks increasingly empty and cold. The acceleration has profound implications. Rather than collapsing back in a big crunch, the universe's expansion will not only persist, but accelerate indefinitely. This leads to an exponential stretching of space itself, which eventually thins out the energy density so much that matter, radiation, and even black holes will become almost meaningless in the grand scheme. Space essentially becomes a vast, silent void. The role of dark energy in shaping this fate adds a layer of unpredictability. Current models suggest that if dark energy remains constant, what scientists call a cosmological constant, the universe will continue its lonely stretch until everything dissolves into dispersed particles and radiation. Black holes, the densest objects in existence, will eventually evaporate through Hawking radiation, releasing their mass back into the universe's energy pool. This process, occurring over incomprehensibly long timescales, ensures that even the most extreme objects will eventually vanish, leaving behind a universe subsumed by entropy. In this distant, fading future, the universe reaches what's known as heat death. Any residual activity halts, no stars burn, no new galaxies form, and the fabric of space-time becomes a featureless, frigid expanse. The temperature drops so low that even particles in quantum fields fall into a state of minimal energy. It's a universe whole in time, where the concept of change becomes meaningless and only silence prevails. This ultimate state reflects a universe that has run its course, where expansion pushes all matter into a quiet, eternal darkness, marking the end of all known physical phenomena. The thermodynamic fate of the universe. The concept of the universe's heat death hinges on the principles of thermodynamics, particularly the second law, which states that entropy, or disorder, in a closed system tends to increase over time. As the universe expands, energy becomes more evenly distributed across increasing volumes of space. Over vast stretches of time, this process leads to a state where no usable energy is left to perform work. In practical terms, stars burn out, galaxies drift apart, and the cosmos approaches a state of maximum entropy, where everything is thermally uniform and energy gradients are eliminated. This results in a universe that is effectively cold, dark, and inert, with no physical processes capable of sustaining complexity or life. In a universe approaching heat death, the scale of energy transfer becomes negligible. The once dynamic interactions between particles, stars, and galactic structures slow down and fade. Matter exists in a thin, diffuse state, spread out so uniformly that gravitational attraction becomes insignificant. Cosmic microwave background radiation, which is residual heat from the Big Bang, gradually cools down to near absolute zero. The entropy of the entire universe reaches its peak, meaning that energy is no longer capable of doing work. Instead of energetic exchanges or formation of new structures, the cosmos becomes a vast, silent expanse. Some physicists believe that black holes, if they persist amidst this long-term scenario, will eventually evaporate via Hawking radiation, further contributing to the universe's cooling and dispersal. This eventual decline into homogeneity is not just a matter of aesthetics or poetic despair. It is rooted in the fundamental laws that govern all physical phenomena. As time extends toward infinity, everything tends toward thermodynamic equilibrium. Without energy differentials, processes such as star formation, planetary geology, or any form of biological activity cease entirely. The universe sustains only a faint, ever-dwindling residual heat. The notion that dark energy, driving the accelerated expansion, shrinks the universe's observable horizon also intensifies this fate. Galaxies beyond our reach accelerate away so rapidly that, in the distant future, they become forever invisible, leaving isolated pockets of matter stranded in the vast emptiness. Standing at the edge of this grand, slow-motion end, one might consider the implications for existence itself. The heat death represents a state where time becomes meaningless, as all change halts. It's a paradoxical situation. The universe doesn't end abruptly like in fiction, but gradually loses all its vitality, dissolving into a uniform, unchanging sea of particles. If entropy is the ultimate fate, then the universe's final chapter isn't marked by destruction or chaos, but by stillness, an eternal silence where the cosmos is no more than a cold, featureless field. This misunderstanding of eventual cosmic fate underscores the importance of thermodynamics, because it ties everything back to fundamental physical laws that govern the evolution of everything we observe, from the smallest particles to the grandest galaxies. The concept of heat death and entropy maxima. The notion of heat death is rooted deeply in the second law of thermodynamics, which states that in an isolated system, entropy tends to increase over time. Entropy, often described as a measure of disorder or the number of microscopic configurations that correspond to a macroscopic state, is constantly rising. As the universe evolves, energy becomes more evenly distributed, and the differences in temperature that drive processes like heat transfer diminish. Over vast stretches of time, this gradual march toward equilibrium results in a state where no thermodynamic free energy remains to perform work. The universe essentially reaches a state of maximum entropy. In this state, often referred to as thermal equilibrium, everything cools down to a uniform temperature, which, in the case of the universe, approaches near absolute zero relative to its initial energy densities. This scenario implies that processes dependent on temperature gradients, like stars shining, galaxies forming, or even atomic interactions, come to a halt because there's no longer any energy flow. Instead, the universe becomes a vast, diffuse, and silent expanse where particles drift aimlessly and no meaningful change can occur. It's a kind of cosmic stillness, an endpoint where chaos has fully spread and ordered structures disintegrated into uniform disorder. Considering the universe's expansion, this concept becomes even more profound. As space stretches, matter becomes more dispersed, and the energy per unit volume decreases. The ultimate outcome is a universe filled with sparse photons and particles that are so spread out that interactions are practically impossible. Black holes may persist for a time, slowly evaporating via Hawking radiation, but eventually, even these remnants vanish, leaving behind a dilute, cold, and silent universe. Entropy reaches its zenith, not because of a sudden event, but as a natural result of cosmic evolution, with the universe inching toward a thermodynamic dead end. This process also highlights the irony that the same laws that give the universe structure and order, like gravity and thermodynamics, inevitably lead to its decay into these quiet, featureless conditions. The heat death highlights a universe where all energy is so evenly distributed that nothing can happen anymore, and all progress or activity halts. It's a future defined by the stark dominance of entropy, a state where the fabric of space-time itself is frozen in eternal uniformity, marking the logical conclusion of cosmic history through the lens of thermodynamics. Implications for the future and humanity. As the universe approaches the theoretical end point known as the heat death, the implications for humanity and our future seem almost poetic in their stark finality. In this distant future, the universe will have expanded to such an extent that all matter is evenly distributed, leaving no gradients, no energy concentrations. Stars will burn out, black holes will eventually evaporate via Hawking radiation, and what remains will be a cold, dark, inert expanse. For humanity, if we are still around at this stage, it means facing the reality that our cosmic environment has become utterly uniform, with no possibility of energy gradients to sustain life, motion, or consciousness as we understand them. This scenario forces us to confront the limits of existence itself and consider whether anything besides fleeting moments of awareness can persist. The potential consequences for human legacy are profound. Our efforts to reach beyond Earth, whether through space exploration, colonization, or technological advancement, are motivated in part by a desire to escape the finite confines of our planet and avoid the eventual silence of the cosmos. Yet, in the long-term view of the universe's course, those ambitions might be seen as temporary sparks in an overwhelmingly silent universe. Nonetheless, these endeavors could yield enduring cultural, scientific, and technological achievements that transcend the physical universe, especially if some form of information transfer or consciousness transfer becomes possible. Human civilization could, in theory, encode knowledge and values in ways that outlast the stars and survive into some future state, essentially making a mark on the cosmos even as its physical structures fade into darkness. On a more philosophical level, contemplating the heat death raises questions about purpose and meaning. If all energy disperses and systems reach equilibrium, then, from a purely physical standpoint, life and consciousness have only temporary windows to exist. This can inspire a sense of urgency or a desire to find meaning within limited timescales. Perhaps, in the face of indefinite silence, human beings might embrace creativity, relationships, and discovery with even greater intensity. Many argue that the fleeting nature of consciousness adds value to life itself, turning our finite moments into something uniquely precious. The awareness that everything will eventually fade can push humanity to treasure what we have now, even as the universe drifts into its cold and silent final chapter. Ultimately, the long arc toward heat death challenges us to think about legacy, what remains when everything else is gone. It encourages a perspective that, despite cosmic futility, meaning can still be crafted through human effort. Whether it's in digital archives, cultural heritage, or even hypothetical future consciousness, some hope persists that our existence can have ripples that extend beyond the physical universe's lifespan. This idea fuels ambitious projects and philosophical debates about our place in the cosmos, and whether, in some distant future, traces of humanity might still whisper through the void, an echo of life in the vast silence of an eternally cooling universe. Usnovnoy, Rusgil 5. As the universe continues its relentless expansion, the concept of heat death emerges as a chilling, inevitable conclusion. Over unimaginably long stretches of time, stars burn out, galaxies drift apart, and energy disperses to the point where thermodynamic equilibrium is achieved. In this final scenario, all processes that produce usable energy cease. Everything cools down to near absolute zero. Without energy gradients, no work can be performed. The universe becomes a vast, silent expanse of uniform temperature, lacking the dynamic interactions that animate its early life stages. The primary driver behind this eventual silence lies in the second law of thermodynamics. It suggests that entropy, disorder, tends to increase over time, leading systems to a state of maximum entropy where no energy gradients remain to sustain processes. As stars exhaust their fuel and no new stars form, matter gradually disperses, becomes sparse, and their radiation drifts into the void. The universe becomes a cold, dark canvas where photons and particles are so spread out that interactions are virtually non-existent. In this state, even phenomena like cosmic background radiation are so diffuse that detecting any meaningful activity becomes impossible. This slow march towards thermodynamic equilibrium isn't just a distant, abstract idea. It has real implications for the future of cosmic structures. Black holes, the most fascinating remnants of stellar evolution, will also slowly evaporate via Hawking radiation. As they lose mass and fade away, the universe becomes dominated by low-energy particles, essentially nothing more than empty space. The timescale for heat death, the period when the universe reaches maximum entropy, is staggering, vastly exceeding any current human lifespan or even the current age of the cosmos. Still, understanding this process provides profound insight into the finiteness of existence and the eventual quietude that awaits. Eventually, after all stars have extinguished, all matter is sufficiently dispersed, and radiation has stretched to such long wavelengths that detection becomes impossible. There will be no bright galaxies, no cosmic fireworks, only the hauntingly still and silent universe, filled with diffuse particles and faint residual radiation. In this universe, time continues to tick forward, but nothing remains to perceive or measure changes. It is, in essence, complete and utter silence, an eerie, tranquil end to the cosmic story of energetic activity. As we reach the final moments of our journey through the universe's ultimate fate, it's clear that the heat death symbolizes the quiet, inevitable end where everything fades into a silent, cold expanse. The universe, with all its vibrant galaxies and energetic phenomena, gradually disperses until no organized structure remains, only a deep, endless calm. This concept challenges us to think about our place in this vast cosmic story, reminding us of the fleeting nature of our existence amidst such immense forces. Thanks for exploring this profound topic with me. It's a reminder of how small yet meaningful our moments are in the grand cosmic ballet. If you're curious to dive even deeper into the mysteries of the universe or explore other mind-bending ideas, stay tuned. There's plenty more to discover together. Until then, keep marveling at the universe's wonder and first look forward to our next adventure into the unknown.